similar topic, but now moving beneath the surface of the ocean. The next speaker is Russell Wynn from the National Oceanography Centre, Southampton.
Thank you, and good afternoon, everyone. So, I'll come to the image in a minute. So, the National Oceanography's role in this space is very much, as we've heard today, we desperately need data, information and technology innovation, and that's where the NOC comes in. My role in NOC recently has been as Associate Director for External Engagement, but also as Chief Scientist of Marine Autonomous and Robotic Systems. This is actually my last public presentation as a NOC employee. I'm following my heart and going into the wildlife conservation sector at the end of the year. So I'll try and hold it together, and it's really nice to be able to do a double act with Dan again. I put that image in before the general election was called, actually, when I first started putting this presentation together, and we're now in Perda, and I think I'm on camera, so I'm not going to make the quip that I was going to. I did have a witty remark. I'll let you guys come up with your own caption there, but I did put it in to remind me to thank Terry on behalf of the conveners for inviting me to come and talk to you this afternoon. So I'm going to talk about marine robotics beneath the surface and where we are with them. We've heard a lot today, so I don't need to do a lot of intro about the drivers behind why marine robotics are a good choice for use in the ocean and what benefits they can provide and what the challenges are. Just around seabed mapping, we've heard quite a bit about that today. Seabed 2030 is a project where the aspiration is to have the world's ocean mapped with modern multi-beam by 2030. It's pretty ambitious, but it's made a really good start, and it's starting to source data from a wide range of vessels equipped with multi-beam systems, both science, industry and others. But the key thing is it's reliant upon vessels at the moment with multi-beam, and most of the ocean is deep water, and there are simply not enough vessels to achieve that vision by 2030 in operations days. So underwater unmanned systems are inevitably going to have a key part to play in doing this. And we've seen things like the Shell X Prize, where new innovative methods of quite high-speed seabed mapping with unmanned underwater systems have been developed and are now starting to become operational. The other thing that struck me this morning was, there's an issue here around the public perception of the maritime sector and some of the industries that we've been talking about today. And public perception and the way in which the public is influencing policy is changing really, really quickly, and social media and dissemination of information is having a key part of that. And we hear a lot about this phrase sea blindness, and I think that if the public were aware of how degraded and a poor state that most of our seabed was in, largely due to commercial fishing activity, which has an order of magnitude spatially bigger impact than any other sector on the seabed, I think they'd be absolutely shocked. Gordon gave some good examples of where we are with satellite imaging of the Earth, and those images are getting through to people to drive home the message of deforestation in areas like South America and Indonesia, and people quite rightly are getting exercised about it, and political pressure is starting to be brought to bear. I think at the moment people are totally unaware of how degraded most of our marine environment is. Just look at the seas around the UK. It's a pretty barren continental shelf that only a few generalist species are really able to occupy successfully. And unless we put in fully protected marine reserves, we're not going to get back to recovery to the kind of ecosystem that I'm going to show you in a minute that we probably did have a lot more of a few hundred years ago. So I think things like Seabed 2030 have a really important role in supporting activity in the marine environment, but also raising the public's perception of particular issues that really need to be addressed. And autonomy will have a key part to play in that. We've heard a lot about these two. Remapping is part of that, but the other reason for flagging these is that things like the UN decade are really going to bring home the need for sustained observations from the ocean. We've heard quite a bit about this today. And here we're starting to talk about decadal scale observations, and that is challenging. It's costly using conventional methods. Research councils don't like funding that type of sustained long-term observation because it doesn't yield fast, quick results that are easily measurable, but it's absolutely vital. When you hear about sea levels going to rise by X by 2100, or the ocean temperature has gone up by this amount in the last 50 years, it's those long-term observations that have been absolutely key to delivering that. And again, autonomy, surface and subsurface, is going to have a key role in delivering that. So where are we today? So this image of the Atlantic, you saw earlier the Argo float network, which are the yellow dots on here, and we have tide gauges, we have ship-occupied sections like the Atlantic Meridional Transit, which runs from the UK down to southernmost South America. a whole series of things that have been done in reasonably conventional ways for over a decade or so now. But what we're finding is that they're still not giving us the quantity and the quality of data that we need to tackle all of the challenges that we're facing. To give an example, the image in the top right is a cross-section of the Atlantic, illustrating the different parts of the Atlantic overturning circulation, which is a series of currents that are really the heartbeat of the Atlantic Ocean that transport not just water around the Atlantic, different water masses, but also really important in transporting heat and carbon, including some of that excess heat and carbon that we're generating through anthropogenic activity. We need to really understand that heartbeat to understand what's going to happen to the Atlantic Ocean in the future and the ecosystems within it. So we have arrays of moorings that go across the Atlantic. There's one you can see on the image on the left at 26 North, that's a rapid array. We have another one at 57 North called the Oceanographic array. And those series of moorings at the present day are collecting data, but we only get that data back when a ship goes out and uploads the data from the subsurface mooring array. And that might happen every few months to every few years. So it's not very high fidelity data. The image bottom right is a wave glider, unmanned surface vehicle. We've been running a project, a science project, where we've been looking at using that vehicle to go and upload data from the rapid array without any ship in the loop at all, and actually looking at, in the long term, having a series of wave gliders going up and down and continuously uploading data from the rapid array and squirting it back via satellite to end users. Why is that important? Well as making sure that we're canning that important data, which is giving us information about long-term climate change impacts on the ocean, there's evidence that things like changes in the overturning circulation on a year-to-year basis have impacts on our seasonal weather patterns. So when that Atlantic overturning circulation is a little bit weaker, it looks like it has a knock-on effect, and there's potentially a colder winter in northwest Europe subsequently. If we can start getting into a predictive mode with that by getting high fidelity data, that starts to become really powerful and useful in an operational sense. And then the little inset map there shows a number of marine protected areas which are proliferating not just around the UK but globally, but we need to understand what's in those marine protected areas and are the protection measures actually making any difference or not. Otherwise there's no point investing time and money in protecting them. And again, submarine autonomy is going to have a key role, and I'll give you some examples of how we measure and monitor these protected areas. Some of you have seen this slide before. This is within English water space. It's the upper part of a large submarine canyon system called Whittard Canyon, and there's a new marine conservation zone called the Canyons Conservation Zone in the upper reaches of this canyon system that extends from the continental shelf down to about 4,000 metres water depth. The point cloud in the background, the 3D point cloud, is ship-based multi-beam bathymetry. Because of water depth, it's not particularly high resolution, just a ship-based multi-beam. The block of denser colour is an AUV map, where the AUV, which is the Ultrasub 6000 vehicle in the inset there, it's a propeller-driven unmanned underwater vehicle that went along a sort of grid pattern, mapped the seabed. But what was novel about it was it actually did it within this submarine canyon and was able to sideways map the vertical or near vertical walls of the canyon by having the multi-beam mounted on the side of the vehicle. That's something that we developed with our engineers at NOC that had never been done before at a global scale, and it gave us this beautiful 3D perspective of this canyon. Why is that important? This canyon holds ecosystems that are fully protected from fishing because of the topography, and they're ecosystems that give us a little bit of insight about what most of our continental shelf might have looked like before it was pretty much wholesale destroyed by trawling and other activities. It's a little bit like if you look at the landscape of lowland England, for instance, little pockets like where I live of the New Forest of ancient woodland are what most of southern England probably would have looked like, and all we've got left are these tiny little pockets now. But we think about that wider landscape of fields and things as being that's the English countryside, but it's not. It used to be a big forest and it's all gone. Pretty much the shelf would have been covered by a much more vibrant ecosystem, and we just have these little pockets remaining that are protected. And tools like the Autosub, by being able to go in and map those in 3D and then target where a remotely operated vehicle can go in and collect high resolution images, are giving us the evidence base to show these are vibrant areas, and when you protect them there's lots of life there, including nurseries for small fish that then go on and seed the commercial fisheries that we all benefit from. So this evidence base that these tools are helping us gather is really, really important, and marine protected areas are just one component of that. And similarly, if we go to northwest Scotland, a couple of stories from an expedition that NOC and partners from DEFRA Group and elsewhere were involved in last month. was going out the Darwin Mounds. They were found in 2000 with a towed side scan system on an EIA for oil and gas actually, and they were heavily degraded by trawling, and as a consequence they were very quickly protected from trawling. And what we've been doing is going back and doing very accurate repeat surveys with an AUV, including photo surveys with the AUV, to work out, is it recovering? You know, we're now 2 decades from closure, is there any recovery? And what we're finding is that in a lot of the areas that were degraded by trawling, there isn't recovery on the time scale of 2 decades. There might never be, the conditions may no longer be suitable for the kinds of organisms that previously lived there. So again, let's protect it first and take the precautionary approach, because if you don't protect it and it gets damaged, it may be that you can't just expect recolonisation to happen like that. It may take centuries or not at all. We've also been testing new sensors on the AUV so that we can image the seabed in ever greater resolution. A biocam system was on there that was developed by colleagues at University of Southampton that generated this fantastic 3D image of a whale carcass out in the northernmost Rockall Trough, mounted on the Ultrasub 6000 vehicle. So we're really trying to push the boundaries. AUVs are pretty commonplace now for doing industry type surveys and science missions, but we're trying to keep pushing the boundary further as to where they go, what they can do, and the resolution of data that they can collect. One of the issues with AUVs, I came up with this phrase last week when we had our Marine Autonomy and Technology Showcase, is that the batteries, the bandwidth and the bomb-proofing haven't moved on much in 10 years or so, I would argue, when it comes to submarine autonomous systems. And for vehicles like Ultrasub 6000, they get pre-programmed with a mission, they go down, they do that mission, and then they run out of battery after 2 or 3 days, and you have to bring them back up to the surface, onto the mothership, recharge, download the data, and go again. That's not very time effective and cost effective. If those vehicles could do several weeks or months, it would be much more time and cost effective, and it potentially take the mothership out of the loop because they could transit out from a shore base. Some people have tackled this challenge by going very big. So this is the Boeing Echo Voyager. It's a 51-foot unmanned underwater submarine, largely targeting, I suspect, the defence customer, because they're probably the only ones with pockets deep enough to buy one of these. But that's one approach, is you go really, really big, and you can also use this as a mothership for smaller unmanned underwater vehicles for a number of different purposes. At the NOC and elsewhere in Canada, US, the approach is to try and develop ultra-long range AUVs that have an endurance of weeks to months. And you do that by being smart with the engineering, looking at optimising the batteries, running them relatively slow. These things aren't zipping around the ocean, they're doing maybe walking pace, but they can do it for several months at a time. And what that does is it starts to open up new areas where we urgently need data. The deep ocean is one. As I say, you don't want to keep coming back up and down from 6,000 metres if you can help it. And for things like deep sea mining, that nascent industry, if it really starts to develop, long endurance AUVs down at depth, monitoring what's happening, doing environmental impact type work are going to be absolutely key, and you don't want to keep bringing those back up to the surface. So these types of long range AUVs can have utility in that space. Also, the other real hotspot that I see coming up in the next few decades is going to be the Arctic. As it opens up, there's going to be a whole range of activities. There's going to be an upsurge in defence and security activity in that space. And those countries that can have a persistent presence in the Arctic are going to have an advantage. And that may be to identify where resources are, it may be to manage those resources, it may be to secure water space, to secure resources, etc. So there's a whole raft of reasons. We're interested on the science perspective because as the Arctic starts to change, it really is changing very quickly, there's a whole load of interesting science to do, and we need to be able to get in there under the ice and in ice marginal areas with assets like this. There's actually a World Climate Research Programme Polar Challenge to do the first unmanned underwater mission under ice in excess of 2,000 kilometres. Our aspiration is to use our own Ultrasub long range, aka BOTI, to do a full Arctic under ice mission from one side of the Arctic to the other, which has never been achieved with an unmanned platform before. So that's where we're going with this kind of technology, and how it opens up the exploration of parts of the Earth where we literally have no or very, very limited data, but it's going to become crucial in the coming decades. Under ice, in terms of navigation, we're having to develop elegant solutions, engineering solutions like train-based navigation, which I won't go into detail here. In open water, one of the challenges, well, how do you get data from a persistent AUV that's down at depth back to an operator in a timely fashion? And one of the ways we're looking at doing that is working with Sonodyne, ASV and others on projects where we actually use a surface vehicle as a gateway, an information gateway between the submarine vehicle and an operator back at shore via the SAT network. I really welcome the talk on the satellite capabilities going forward. So I've long thought that actually we don't exploit information from the cloud and from satellites well enough. We tend to load lots of sensors onto these vehicles to give them situational awareness, but actually there's a huge amount of data there to access that we just need to work out how to get it down into the vehicle to improve collision avoidance and such like. So that was really good. And we've been looking at doing this by combining different types of vehicles and even unmanned aerial vehicles so that you get that full picture from the seabed to the sea surface into the lower atmosphere as well. Part of the job of the NOC and part of my job has been to think about how do we get across to the public that these things are a force for good. I'm very conscious that the unmanned aerial vehicle space is a series of unhappy media stories over the last few years, and I've been very keen, as part of one of the largest fleets in Europe, if not the world, to make sure that we don't fall foul of the same negative publicity. And I think that's of interest to anyone working in this sector. So we've worked very, very hard at our relationship with the BBC, for instance, and the science editor David Shukman and Jonathan Amos to go on a journey where we're looking at platforms like BOTI doing exciting stuff where they can engage early and run positive stories about those platforms. And the other thing, as Dan mentioned, that I wanted to do early in my time as Master Chief Scientist was have a mechanism where we could get these platforms in the water, put them through their paces. NOC is an independent organisation, we don't sell stuff, but we can put trials on and invite people along to those and see what these things can do in real world situations in the ocean. And they've been really beneficial to potential end users like the Navy, who are inherently conservative and need to actually see this stuff happening to believe it and to uptake the technology. That said, we're still a long way behind the best in the world. I would argue that Woods Hole and the way that they do their outreach and their public engagement is a long way ahead of us, but it's something we want to aspire to. Things like their Shark Cam, if you've never seen that, go and Google it and have a look at it. It's absolutely amazing. You know, Remus AUV armed with GoPro cameras tracking great whites to look at their habitat use and behaviour. AUV gets attacked by the great white. It's just brilliant. Gives my Mars head colleagues absolute nightmares and cold sweats. And we do have a glider that was out in the Bahamas last winter that now has a nice shark bite in the side of it. So the interesting thing working with the likes of BP and the Navy has been this conservatism and this sort of momentum that they have around normal conventional ship-based operations. In the later phases of MASMO, we started to put in some new technologies like micro-AUVs. The EcoSub is the example that you can see in the image here, and actually operating them from Navy vessels themselves. And that really empowered them, and they got to see the benefits of the data coming off and starting to be able to use that data for themselves. Things like the EcoSub, we've been working with University of Southampton to look at air launching them into theatre, into dangerous and hazardous locations. Someone mentioned Deepwater Horizon earlier. I'd imagine that if in 5-10 years' time another Deepwater Horizon happened, BP would have a fleet of UAVs with a fleet of micro-UAVs with hydrocarbon sensors that are intelligently networked that they would just drop into theatre instantly at a fraction of the cost of the infrastructure that was mobilised last time around when Deepwater Horizon kicked off. So it's really going to change the way in which we deal with emergency and rapid response to environmental incidents. MASMOs have got more ambitious. As I mentioned, we started to use fleets of vehicles working together. The image on the left is a submarine glider, which are again slow vehicles that oscillate through the water column like this, collecting oceanographic data of various types. The image top right shows what happens when you put a whole fleet of these out in the ocean. We covered about 5,000 square kilometres of ocean northwest of the Outer Hebrides with data in a 2-week period in advance of the Navy's unmanned Warrior. To do that with vessels in what was pretty stormy conditions at the time would A, have been uncomfortable and B, really expensive. So again, that really opened the eyes to the Navy of what you can do. And we've worked a lot on the mission control so that from my phone I can see where all of the assets are during a mission like that. I can overlay data layers like tidal prediction currents, bathymetry, satellite information, and it gives me real power as a chief scientist to guide what the assets are doing and use that fleet in an intelligent way to get the most out of it in the time available. We're looking at developing gliders now that can go down to 6,000 metres. And we're looking at assets that can start to hibernate on the seabed to measure things like seasonal change. So that you put something on the seabed, goes to sleep for a few months, it wakes up and it makes a measurement in the spring through the water column, goes back to sleep again, ditto repeat in the summer, autumn and winter. Obvious science utility, obvious defence utility is sunning quiet, sleeping on the seabed as well. So lots of opportunities with these new long endurance deep vehicles. This should be the other way round, but we can work with it. So we're also getting gliders to the point where they're starting to do seasonal change. And they can occupy areas such as in this case the North Sea for up to a year at a time, looking at seasonal change of things like plankton blooms, temperature, water column structure, etc. So just to guide you, if you look at the one on the left, this axis here is depth from 0 to 100 metres, and then this is time in months, so it's about a year, just over a year I think. And you can see the warming of the surface waters in the summer, which are the hot colours, the red in the surface waters. And then you can see the plankton bloom in the middle panel occurring around the spring in there. And then I think the bottom one is another parameter, might be oxygen. But we're starting to move towards this long-term monitoring capability. The only ship requirement was to get the assets in and out of the water. And over time that will go away as well. So you're starting to move towards a ship-independent monitoring system of the health of UK seas that could be applied globally. And that's really helping DEFRA, who at the minute are very ship poor. They have the CFAS Endeavour, but that's about it really within their fleet in English waters. So these gliders and this capability is giving them extra opportunities. To finish up, I just want to make the point that we don't look at marine robots as a system in isolation. They're not the be-all and end-all. They're just one part of an observing network that really needs to be brought together in what the defence colleagues call best composite picture to get the most out. What we really want to do is say, let's take a cube of ocean and really understand what's there using all of the different data types available to us. So these are some MASMO data from a couple of years ago off the Northern Isles. And what they're showing is seabed bathymetry, modelled tidal currents, the arrows, the red and blue stripes that you can see there are satellite imaged fronts provided by our colleagues at PML, and then the glider data, which in this case are measuring salinity, are the sort of linear blocks of data that you can see over here. So you can see that the glider data are picking out two water masses of different salinity, either side of a front that's imaged by satellite, and the data are lining up very nicely. Two different sources, they've each got different strengths. The glider data are helping calibrate and ground truth the satellite data, and the satellite data are giving greater spatial context to that block of glider data. So this fusion of model, remote sensing and autonomous platform data is really powerful. And to give one more example of that, another MASMO, this case going into the Ferret Shetland Channel from the shelf down into the deep water over 1,000 metres deep. These are a series of glider tracks on the surface, these coloured lines. This purple layer is the modelled thermocline, an important water mass boundary coming out of the Met Office foam model. The glider data that were in situ and sending the data back in real time via satellite were picking up the thermocline where those black dots are, and you can see there's an offset. Why is that important? The thermocline is strategically important in the defence sector because it's a really key acoustic boundary. It's also important because it's a biological feature where you often get high concentration of biota. So understanding where that is in real time can be quite important for everything from defence, anti-submarine warfare to fisheries, etc. So again, this fusion of glider data and model data to improve best composite picture, I think, is going to be absolutely key going forwards. And it's been great to be able to demonstrate some of that, in this case to the defence end user in the Navy and Defence Science and Tech Lab. So finally, again, just to bring home that point, we really need to rely, to meet the challenges of data from the oceans, on not just marine autonomous systems, but all of the existing infrastructure that's already there, ships, buoys, seabed moorings, Argo floats, but also those things that are coming in from satellites and from models, and bring all that together to get that best composite picture that gives us the best data set and the greatest confidence in what we're looking at. And only then are we going to be able to really start upscaling the amount of data available to meet the challenges that we've got. And I started with a quasi-political image. I'll finish with one. This was from a couple of years ago, and I think unfortunately probably life hasn't moved on that much in the last couple of years, but I'll let you guys make your own minds up on that. Thank you.